Okay, so welcome to a lesson about modeling real-life phenomena. And today we will look on cubic models. And the lesson will continue like this. First, I will show you something in general about cubic models, some important concepts about it. And then I will show you two examples from real life with regards to important things to take in consideration when you're dealing with cubic models. And then finally, I will show you an example where we use our calculator to answer questions about cubic models. So you need to have your calculator with you. So if you don't have it, you can take a pause now and get it and then start again. And as always, you can take as many pauses as you want to. If I'm writing too fast or something and you want to catch up with me, you take a pause. And if I'm writing too slow or talking too slow, you can maybe speed it up or something. Okay, so let's start with cubic models in general. So, in general, a cubic model looks like this. It's a function. It's a function that depends on a variable. In maths, we normally use x. And it looks like this. ax cubed plus bx squared plus cx plus d. So, this is a cubic model. It's a cubic model because the highest exponent is 3 cube. If we didn't have that term, but this term, then it would be a quadratic model. And in real life phenomena, we have different values on the constant A, B, C, and D. That's what's changing in different models. Now, A, the constant A, is not allowed to be 0. Because if it is, then you have 0 multiplied with x cubed, then this term is 0. Then there is no cubic model anymore. B and C and D, these three constants, they all, and I don't know if you have seen this symbol, it looks like an E. You pronounce it, belongs to. The constants B, C, and D belongs to the real numbers. An R with an extra line like this. The real numbers. So A is also a real number except for 0. Then we say this is a cubic model. So B and C and D could be 0. That's okay. So the first example I would show you where we use the cubic models in real life, then B and C and D is 0. So let's write it down. Example. Power of a windmill. The power, the energy you get from windmills, you will get it as electricity into your house. And the power from it, capital P, depends on the velocity of the wind. And it's a function, and you write it like this. 0.297 times A times rho times the velocity cubed. So this is the model for describing the power. It's a function of the velocity of the wind with no more terms. So B, C, and D are 0 here. Now, A stands for the area that the blades in the windmill is sweeping over. Therefore, you see larger and larger windmills. The longer arms the blades has, the larger is the area. And the larger the area, the more power you get from it. You also have the density of the air. So the higher the density, the higher the power. But the density of the air is quite the same. You can't change it. But you could put the windmill in water. Then you might call it a water mill instead. Water has a much larger density than air. Therefore, the power is bigger when you have the windmill in water instead. So they are doing research right now about building windmills in water. But you don't call them windmills then. And the power also depends on the velocity, and the velocity is very important. I will show you that later on. It's so important, so you have to take it in to the power of 3. If you are studying physics or an engineering program, they will explain for you why you take it in cube like this. I will not do it now, but I will show you what's happening when you cube something like this. You also have a constant here, 0.297. It's a constant that depends on the geometry of the blades. And this constant is the highest possible constant. This is the highest power you can get from a windmill with a certain area, certain density of the air, and in a certain velocity of the air. But the constant can be smaller also. Okay, a little bit of windmills. I will come back to this 3 and explain something more about it. But we continue with another example, and I will start with a question. And the question is, why no bigger animals than elephants? And that's a question. So, why don't we have any bigger animals than elephants on land on Earth? We have bigger animals like the blue whale in water, but on land, you have heard that Charles Darwin and the laws of evolution says that it might be an advantage for an animal to get big. Then the animal don't have to be afraid of other animals because it gets stronger with the size. So why is there no bigger animals than elephants? You could actually show it with a cubic model. And I will do it for you right now. So, you could actually draw an animal like this. I will draw the animal like a cylinder. And the diameter of the cylinder is 2 squares. And the height of this cylinder is 1 square. That means that the radius of this cylinder, well, I call it R, and the height is also R. This is the height, but they are the same, 1 square. Therefore, I can use the same letter for it, the same symbol. Now, this is a symbol for an animal. You can actually draw them like this. It could be a human, it could be me. It could also be the symbol for the bone inside the legs and arms of these animals. So, in my arm I have bones and they look like cylinders actually. And you already know that the bigger the animal, the bigger the bones they have and the bigger legs they have. So an elephant's legs is huge, and the area of the bone is also huge. And this area of the bone inside an animal gives the strength, in some sense, of the animal. Because the bigger the bone, the more mass it could take and hold up. So the area, it's a circle, you know. So the area of the circle is pi r squared. So the area tells us something about the strength of the bones and also, therefore, the strength of the animal. And the animal, at least this bone inside the legs of the animals, has a volume. And the greater the volume, the more mass it has. So the mass depends on the volume. And the more volume it has, the heavier it will be in the animal. So it needs to be more strong to lift up all the masses. Now, the volume of a cylinder, it's the base area multiplied with the height. And the base is the area of a circle. So it's pi r, look now, r squared multiplied with r. So it's 2r and 1r more, so it's r3. So we see that the volume, you can describe it with the cubic models. The headlines for today's lesson. The volume depends on the radius when you cube it, like this. Now, why no bigger animals than elephants? So if this is the bone inside an elephant or an animal, it could be also the animals itself. But let's see what's happening if we double the length of the animals. So I will draw a cylinder, 1, 2, 3, 4, with the diameter 4 squares. So the radius will become 2r instead of 1r. 2r is the double the length. And then the height will be 2 squares instead of 1 squares. So the cylinder will look something like this. So you have 2r for the height and 2r for the radius, like this. Now, let's see what happens with the area. This area, if you double the radius. So many people would say that if you double the radius, well, probably the area will be doubled as well. But that's not true, because this is what's happening. You will take pi, and then you will take the radius, and you will square it. But the radius now is 2r. And you square both 2 and r. So that exponent 2 is going to both r and 2. So we will get pi times 2 square and r square. That's 2 times 2. That is 4 pi r squared. So if we compare this area, pi r2, with 4 pi r2, well, this area is 4 times bigger. Therefore, an animal with bones that has a radius that's 2 times bigger would become 4 times as strong in some sense, because their bones can hold up a masses or a volume that's 4 times greater. But let's look and see what's happening with the volume. So the volume of these animals, you can see this volume is much bigger than this. But how much bigger? Well, it's pi times r, and you have to take it to the power of 3. Now r is 2r. Because the radius is 2r and the height is 2r, and you take it to the power of 3. Now this exponent belongs to both r and 2, so we will get pi times 2 to the power of 2 to the power of 3 multiplied with r to the power of 3. Well, you know the exponent's law, so 2 to the power of 3 is 2 times 2 times 2. That means that the volume is 8 times pi times r to the power of 3. Now, let's compare these two volumes. Pi r3, but here you multiply with 8. Therefore, the volume and therefore the mass of these animals is 8 times as big in these animals. So even if this animal gets 4 times as strong in some sense, it has to hold up in volume and mass that's 8 times stronger. So it will feel weaker. Therefore, you can't be as big as there is a limit for how big you can be if you not are an animal in water, because the water lifts you up because of the Archimedes law. Okay, so you can see when you double the radius, the volume gets 8 times greater. That's the same with powers of a windmill. If you double the speed or the velocity of the wind, the power will be 8 times bigger. So let's hope for great velocity on the wind. And you can get it by building high windmills, because high up in the air, like 100 meters up in the air, it's always blowing, and the wind speed is greater than on the ground. Okay, that's something about cube and the importance of cubing something and what it implies. Now let's look on an example where we use our calculator and how to find models like this. So let's see. If I just turn the page, I have an exercise for you. You can take a pause now and write it down in your notebook. And when you're done, you start again. And the exercise looks like this. A rock falls off the top of a cliff. Let h be its height above ground in meters after t seconds. The table gives values of h and t, of height and time. So if you want to have a picture of it, it looks like this. You have a rock, it looks like a building, and you have the ground. And you drop the rock. No, this is a cliff. And you drop a rock and it falls down something like this. And you measure the time and you see how it's falling. So as the time goes by, the distance to the ground, it gets smaller and smaller because it falls down to the ground level. Okay, so I will ask you a question about this. And the first one is this. Use your GDC, that's your graphical calculator, to find a cubic model over this. So I want a cubic model where h, the height, depends of the time. So I would like to find a constant that describes the height with the time. And I will show you how you do that with your calculator. So take your calculator. And first of all, we will do some settings here. So you can start by pressing y equals 2. And here you can see I have some old functions. I want to take them away so they don't bother me anymore. So I press clear. And I go down with the arrow and I press clear. So you do it as well, so there is no other functions there. And then you will press mode. And then you will take the arrow down until you reach full, and then you go back even more. And there's a new menu, and you go down to Stat Diagnostics. And there you will take the arrow to the right if it's not already on. And when it's on, you press enter, because this is statistics and we want to diagnose this. Okay, now let's go into stat, this button. So you press it and it says edit, and then immediately you press enter. And here I have some statistics already. I will take it away and write down my information here. So I do like this. I take the arrow up, so it's on L1, and then I press clear, and then I press enter, and then all the numbers goes away. And then I go to the right, and I go up to L2, and I press clear, and I press enter, and all the number goes away. So this is going quite fast now. You can see it many times as you want to later on. Now I go to L1. And on L1, you normally have the X values. That's the independent variable. The time is independent. I can't force it to go faster or slower. Well, actually, I can if I know some physics about speed, but let's not talk about that now. And H is the dependent variable. It will be on L2. It's the Y values. So I'm start writing now. 1, and I press enter. 2, and I press enter. 3, enter. 4, enter. And 5, enter. I have 5 seconds. And for every second, there is a value that belongs to it, the height. So I take the arrow to the right, and I start with, after 1 second, the height of this cliff, or the height of this rock above the ground is 106 meters. Enter. And I continue. So I press 99 and enter. 86 and enter. 63 and enter. And 30 and enter. Now I have my values, and I will ask the calculator to find the cubic model. Then you do like this. You're pressing stat again. Stat. And then we go one step to the right. We want it to calculate. And then I can choose among many models. I can choose a linear function, or a quadratic function, or a cubic function. And we will even go down and find exponential function later on, or power functions. But today we will look on the cubic function. It says cubic reg. It's short for regression. Regression is the method to find this cubic model, this cubic function. So quadreg, it stands for regression. You don't normally know which kind of function it is. So in the beginning you need help, and I will tell you today it's a cubic function. So on cubic I press enter. And then the calculator asks if is the X values on list 1, and it is. So I just go down one step. Is the Y values on list 2? Well, it is. If I did some mistake and want to change it, you see I have L1 here and L2. So I can press, I will show you, I press, but you don't do this. I press second and 1, and then it says L1 here instead. But now I want L2 to be here. Frequent list, don't bother about that. Store reg. I want to store this function under y equals 2. And to do that, you have to press the green one first, the green, and then trace. It says F4 bow here. And then I can choose to store this function under some of these y1 or y2 or y3, and I can see it over here. That's because I want to draw this function later on. So I press enter here, and it's stored under y1. I can choose y2 or y3 if I have something else stored, but we took it away. We started by taking away older functions here. And now I press enter, and I press just enter once more. And I get this constant. So you see, y is equal to a times x to the power of 3, just like we wrote the cubic model in its general form, plus b times x to the power of 2, and so on. So you see, they gives us the values of the constant. And then we have the R2 value. This number tells us how good this function is. It's the best you can have is 1 on the R2 value. And it should really be close to 1, because then it's a good model, a good function. Okay, so let's write it down. This model now, I don't use y, I use h. H is a function of t, and it looks like this. A minus 0.333. So I have 3 significant figures times time to the power of 3. So we use time t instead of x. Plus, but we have a negative value for b. So it's minus 1.43 so I have to round it off, times t to the power of 2. And then I have c, it's negative, minus 0.0952 times t. And the last one, d, plus 107.8. So this is our cubic model that describes the height as a function of the time. Okay, the second question. Write down the height of the cliff. The height of the cliff. You can see it here. This is the height of the cliff. How do you find that? Well, we know that the height depends on the time. And the height is as big as possible when the time is 0, because the time starts here. It's 0 here, and then the time increases here. So we see after 1 second, it's 106 meters above the ground. What's the height after 0 second? We don't have 0 here, but we can calculate it. The height after 0 second, we have the formula here for it. So you realize that if I take 0 here, this term becomes 0. And with 0 here, this term is 0. And with 0 here, this term is 0. So the height of the cliff is 107.8 meters. The constant, the starting value, shows us the height as the time is 0. So you can see after, when it starts, it's 107.8 meters. After 1 second, it has drops only 1.8 meter. After 2 seconds, it has drops 7 meter. Between the first and the second seconds. Between the 4th and the 5th second, it drops 33 meters because of the acceleration. Okay, let's continue. C. Find the height of the rock that drops falling down after 3.5 seconds. Find the height of the rock. Well, you see 3.5 seconds, it's between 3 and 4 seconds, and you don't have any value for that here. You might think that 3.5 seconds, it's in the middle here between, so the height should be in the middle. And that's true only for linear functions. But this function is not linear, it's a cubic function. Therefore, you can't take the middle value here. But we can use our calculator. So, let's look on it. This is the function for it. So, now I just press graph. And I will see what's happening. So, it's a very good window now because I have cheated. I chose the good window before you came here, but I will show you my window. So I click on window, and then I've chosen a window where I start with as the time is 0. Because you drop it when it's 0. And the maximum value for the time, well, it's X here, it's 5 seconds because it just goes to 5 seconds. X scale doesn't matter, you can choose 1, it doesn't matter. The minimum value is 0, it can't go below ground. Well, might be the case, but now I choose 0. And the maximum value I have chosen 110 meters. We know that the maximum value is 107.8, so I take a little bit more than that. And then I press graph, and it looks like this. So it tells us as the time goes by, the height is getting smaller and smaller. It's not the case that you are throwing the stone to the side like this. This is the time. So the stone is falling down. Now, find the height of the rock after 3.5 seconds. Then you want your calculator to do a calculation. You can see calc here in blue text, so you have to press the blue button first and then trace. And then it says value here, and value is the Y value. And it's on 1 here already, so you just have to press enter. And then it asks you, what's the X value? Well, that is 3.5. And then you press enter. And then the calculator shows you here, X is 3.5 and Y, that is the height, is 75.7 meters. So the height after 3.5 seconds is equal to 75, well, I round it off to 7 meters. And 75.7, it's not in the middle between 86 and 63. Okay. One question more here. And that is, after how many seconds is the rock 50 meter above ground? And that is a question. After how many seconds is the rock 50 meters above ground? Well, 50 meters, it's between 30 and 63, so we can say now it's between 4 and 5 seconds. But I will use the calculator to find the exact value for it. Now, there is no method here to, under calc, to find the X value. It's just the value for the Y. If I have plenty of time, I can use this value. I press enter and I guess on 4.5 seconds. And see, well, that's 48 meter above ground. So probably I will choose a little bit smaller value on the time to get 50. But I don't want to guess like this. I will find a method for always finding it. And then you do like this. You press Y equals to. And here you see the function. We saved it, we stored it here. So this is our cubic function. I go down one step and I press 50. Let's see what's happened if we draw the graph now. So we have the cubic function and we have y is equals to 50. And listen now and look now at the intersection between this curve and this line. We have the chime for the intersection. And I will find intersection and the calculator can find it. It's under calc. So you press second and trace. And here you see intersect. So we go down to intersect and we press enter. And then it says first curve. And you could have 3 curves and then you can jump between the curves with these arrows. So you see it's standing here now, mark this place. So if I press down, it jumps here. Is this the first curve? So if you just have 2 curves, you don't have to bother, you just press enter. And then it says second curve and then it jumps up. So it's asked, is this the second curve? If you just have 2 curves, you just press enter 2 times. If you have 3 curves, you have to jump between the curves with the arrows. Now, just press enter. And then it says guess. Because if you have 1 line and 1 curve or 2 curves, it can intersect on 2 places. But if they just intersect on 1 place, you just press enter when they ask you guess. Otherwise, you take the arrow to the right or left, so you stand quite close to the intersection. And then you press enter. And you see intersect as y is equal to 50. And the time is 4.44 seconds. It's a little bit less than 4.48 as we saw when we guessed. So the time is 4.44 seconds when the rock is 50 meters above the ground. It's something here between 4.44. Wow, now you know a lot about cubic models. Thank you for today.